far we've established that 3a allowed us to calculate volumes by slicing. 3c, we're going to use the method of volumes by slicing, but we're going to modify it. In 3a, we were integrating the cross-sectional area we got at a particular x value. We were just using formulas from geometry for that. So that limited us to things like if we could get rectangles or trapezoids or triangles or portions of circles, but I know how to calculate a whole lot more areas. So if we say the cross-sectional area can actually be calculated as an integral, then we end up having to integrate twice. So we'll have the integral from 0 to 1, the integral from 0 to 2 of 3 minus x minus y dy dx. We call this whole thing an iterated integral. It is not necessary to have these parentheses around the inside integral, although often I find it's helpful to draw them in, because by definition we work from the inside out. So we're going to do, that's kind of a gross color marker, we'll get rid of that. Okay, we're going to do that inside integral first. This is finding the cross-sectional area. This inside one is a partial integral. If we're integrating with respect to y, we're holding x constant. We find our cross-sectional area, and then we integrate that with respect to x. That essentially corresponds to multiplying by the thickness of the slice, adding up all the slices, and taking the limit. Pretty cool. Okay, so let's actually work this out. Okay. Oh, one thing to mention about the notation. So I did say that these parentheses are optional. Okay. Also, very, very important, the order in which you write things. Okay. dy, these are my y limits of integration. They go together. dx, these are my x limits of integration. They go together. So very, very important that you make sure that when you're integrating with respect to y, the corresponding limits of integration are your y values. Okay, so I'm going to have the integral from 0 to 1 dx. I find these parentheses helpful because I'm just doing this work on the inside. So I need to take an antiderivative with respect to y. That means y is my only variable. So 3 is constant, so I'm going to get 3y. Minus x is constant, so I'm going to get x times y. Minus y is my variable, so I'm going to get y squared over 2. And that's all going to be evaluated between 2 and 0. So I've got the integral from 0 to 1 of, let's see, that's going to become 6 minus 2x minus 4 halves is 2 minus 0 is what I get when I plug in 0, since there's a y in every term, dx. Notice I was plugging in for my y values. Now what that did, this is awesome. When you integrate with respect to y, you replace the y values with these numbers. So I get something that's just a function of x. I can integrate a function of x with respect to the one variable. So we get the integral from 0 to 1 of 4 minus 2x dx. That should look awfully familiar. That's the formula for the cross-sectional area that we got using geometry. We just got the same formula using integration instead. Very cool. So again, that was just 4x minus x squared, evaluated between 1 and 0. So that was going to give me 4 minus 1 minus 0, which gives us 3, which is what we got when we did it the 3a way. What's nice about the 3c way is that now we're not restricted to shapes where we get something where we can find the area using a geometry formula. So, two big changes. One, we're working with signed volume, which we really didn't go into in 3a at all. So we're allowed to get negative values for our integrals. And two, we're finding that cross-sectional area by integrating.